Hello everybody, this is Conundrum again with an update for the video Calculate the distance to the Sun. Where is the Sun? People have been commenting that some of my coordinates have a small discrepancy, and rightly so, but this is only confined to points that have half a degree in them. How did I find these points? I used Google Earth. I drew a line. I did this manually. I zoomed all the way in to each point and I pulled the line all the way to the Tropic of Cancer near India, and a second line from the same point all the way to the 180 degree east meridian. Yeah, this is how I placed each point, which I placed manually. But you see, even Google, when you zoom all the way in, it becomes a bit hit and miss. Sometimes it's on the line, sometimes it's not on the line, you see? So anyway, I did my best in placing these points manually on Google Earth. Let's see F, for example, which are placed again, by the way. These are new points that are placed today. I find 17 degrees, 3 minutes and 2 seconds north, and the longitude, of course, I type it in exactly. In my previous example, what did I find for point F, let's say? It's 17.3, 17.3 and 14, and now I have 17.3 and 2. Okay, so there is a discrepancy because I did this manually. Is it on the line? Is it not on the line? It's moving, you see? Well, it's placed roughly on the line, you know, as good as I could get it. I inserted the points again on the same circle. I redrew the circle and I placed the points again. Even though what I did was honest, there is an honest mistake in all this. For example, A is at 22 degrees and 50 minutes. These are the points of 2015. Now, if I show you the new points, is at 22 degrees and 30 minutes. Exactly. So it's a more correct point. It's still on the same line. My whole integer points are exactly the same. They're correct. They're on point with the old points. However, there is still a mistake in all of this, which I discovered when I started rechecking the points. There is still a mistake here, which we're gonna correct today. So I decided there must be a way to programmatically find these points with greater accuracy than just visually using the eye in Google Earth to satisfy everybody. I discovered that there are calculators that calculate the ecliptic circle, and they have to do with astronomy. Therefore, we have to deal with something like this. Okay, on this page, it explains the ecliptic, okay? And this is for astronomy. It explains the cycle of the seasons, and it shows us here a sphere which is not the Earth. This is the celestial sphere. It shows us the ecliptic plane in green. It shows us the celestial equator, and it shows us the pole. K is the northern pole of the ecliptic, and K dash is the southern one. P is the north pole, and there's a P dash, which is the southern pole of the celestial sphere, the north and the south, while this is for the ecliptic. You see, the ecliptic is tilted, so the difference between K and P is 23.4 or 23.5. I've seen many different answers for that. So I wanted to make sure that P, the north pole of the celestial sphere, is our north pole, and that the celestial equator is our equator as well, to make sure that the coordinates match. I found this page that says that the celestial equator is a great circle of the imaginary celestial sphere on the same plane as the equator of the Earth. Therefore, if it's on the same plane as the equator of the Earth, it stands to reason that also the north pole of this celestial sphere is exactly our north pole. Okay, so we have the North Pole, our North Pole, the North Pole of the celestial sphere, our North Pole. We have the celestial equator, which is our equator extended outwards. Okay, this is what it says here. Also, to double check that the North Pole of the celestial sphere is the same as ours, true north, also called geodetic north, is the direction along Earth's surface towards the geographic North Pole. Now, what is this? True geodetic north differs from magnetic north and from grid north. Geodetic true north also differs very slightly from astronomical true north by a few arc seconds, because the local gravity may not point at the exact rotational axis of the Earth. The direction of astronomical true north is marked in the skies by the North Celestial Pole. The direction of astronomical true north is the North Celestial Pole. It slightly differs by a few arc seconds from the geodetic north. Basically, north is the celestial north, and the equator is the celestial equator. Okay, so we have that sorted. Okay, now, is there a way that astronomers can find the path of the sun on the celestial sphere throughout the year by an equation? And can we convert the position of the sun on the celestial sphere? Okay, let's see the sun moving around the celestial sphere with our North Pole. Okay, and the celestial sphere North Pole. Okay, this is the path of the sun. Okay, can we take these coordinates and map them on the Earth? Okay, since basically this is what it is. Basically, this celestial sphere can be shrunk down and shrink wrapped around the Earth, and then the sun's position can show us basically the Great Circle. This circle. What we need is a way to map the path that the sun makes on the celestial sphere and project it on the Earth. So we have from the vernal equinox, let's say time 0. This is how they calculate it actually. They use a term called hour angle. Okay, and that's hour 0 and hour 3. Hour 3 is 45 degrees. Hour 6 is 90 degrees. Hour 9 is 135. And hour 12 is 180. So it's like a clock with 24 hours. And we need the path that the sun makes. We need to map it onto the Earth. I found this website and it says determining the ecliptic longitude. The longitude is basically these hours. We know the hours. What we need to determine actually is the latitude, which on the celestial sphere is called the declination. Equatorial coordinates shown by this circle here. The ecliptic is this plane. This rise on the ecliptic for a given angle on the equatorial, say 22.5, creates a wedge. Okay? And this wedge, we can see it here in detail. For a given distance, x1, the ecliptic has to travel a longer distance, x2. So, if at the base where x1 is formed, we have an angle beta, and there's another triangle at the top with an angle alpha on the ecliptic. Which angle is larger? Obviously, alpha is larger than beta because x2 is larger than x1. So for a given angle 22.5, let's say, on the equatorial, there's a larger angle on the ecliptic. Larger angle. So we need a transformation from equatorial coordinates to ecliptic coordinates in order to achieve what we need. We need to convert these 22.5 to an angle x. We need to convert 45 to an angle x1. We need to convert 67.5. We need to convert 90. Okay, 90 is exactly 90. Alright, 90 is the same. But we need to convert our angles to ecliptic angles. And actually, we don't need 22.5 on the equatorial. Actually, we need x to be 22.5. We need x1 to be 45. We need x2 to be 67.5 up here. We need these angles on the equatorial, and actually what we need to find out is what angle this one is on the equatorial. In order for us to find that point and that point, we need to find x, what x on the equatorial is, what x1 on the equatorial is. We need to find what x2 on the equatorial is. We don't know these angles. In order to find the points from where we can take our measurements. So I hope this has been clear. We need a conversion from equatorial coordinates to ecliptic coordinates for these, to solve for these angles. I checked around and I found equatorial and ecliptic coordinate calculators. This is an ecliptic to equatorial coordinate calculator. If we type in 0 as longitude and 0 as latitude, it will give us a 0, 0 position. So a 0, 0 position would equate to the point Z1. That's a 0, 0 position. How about a D position, which is 90 degrees? That would equate to being 90 degrees away from Z1 and positive declination from the equator of 23.26. 23 degrees and 26 minutes north. So point Z1, point D is correct. Now if we go to 180 degrees, we get that's 180 degrees on the opposite side of Z1, and the declination is 0 because we're on the, that's the vernal equinox, that's the autumnal equinox. Okay, that's fine. And we go to 270 degrees, that's on the opposite side of D, there, exactly there. It says that's 270 degrees, exactly there. It says declination, it's negative 23. Yes, because under the celestial equator by 23 degrees and 26 minutes. Perfect. What about the in-between points now? Let's check point B. Point B is at 45 degrees from Z1, and we're looking for its latitude. So if we enter 45 degrees as longitude, it comes up with a declination, a positive declination, that's an elevation of 16 degrees and 20 minutes. So we need new points. Why? Because of the equatorial problem. Let's place a point D dash, let's call it D dash, okay, and let's place it at 0 north and 90 east. There it is, D1, D dash. Okay, now would you agree with me that if both these points are right on the edge of the Earth there, that the distance between here and each of the points is equal, okay, as the distance between Z1 and the North Pole, between Z1 and the South Pole, between Z1 and D dash, between Z1 and D, between Z1 and each point on the circumference of the Earth, okay? Now, since they're equidistant between them, it means that they form an equilateral triangle between them. Yeah? Z1D, Z1D dash, equal distance, so equal angles. They are at 90 degrees with the center of the Earth. Z1D, center of the Earth, same angle as Z1D dash and center of the Earth. They're equal slices. Okay. However, that cannot be said for a point A and a point A dash. Let's draw a line. Okay, and let's say that we start from 22.5 degrees on the equator, and we follow this line straight up on the meridian. The distance between Z1 and this point is not equidistant with Z1 and A. Obviously, there's a larger angle involved here between Z1 and A and the center of the Earth. That's a greater angle than Z1 and A dash and the center of the Earth, which must be a smaller angle. So A, even though it's on the 21.5 degree meridian, its angle with the center of the Earth and Z1 is much larger than 21.5, and this is the problem that I have to solve now, because the slices that I used here, they're not correct. These 22.5 and 45 and 67.5 degree angles, they are not correct when it comes to the ecliptic plane of the Earth. They're correct for the equatorial plane. Yes, they are continuations. They are continuations of the 22.5 meridian, and that's where they meet the ecliptic plane. But on the ecliptic plane, they do not form a 22.5 degree angle. They do not form a 45 degree angle. They form larger angles, actually. This, for example, from Z2 to G is larger than 21.5 degrees. It was, the idea was correct, but the mathematics are not correct, and I have to admit that now. It wasn't intentional, obviously. It was assumed. It was wrongly assumed. Yes, and we should be careful of assumptions, of course. So nobody brought this to my attention, but at least I found out, and I want to correct this because I don't like leaving loose ends. So how did I go about to finding new points? I found new points. Okay, now these are the 2015 points. These are the updated, corrected points for the half angles, which are still wrong. And if I remove the old ones and leave the new ones in, and these are the new points that are exactly correct. You see, for Z1 to A forms an actual 22.5 degree angle now. Z1 to A instead of the old A now forms a 22.5 degree angle with the center of the Earth. That is a wrong angle. It's larger on the ecliptic. The same goes for B. From Z1 to B is a true 45-degree angle on the ecliptic. The old B made a larger angle on the ecliptic. And the same goes for C. C should be further to the left in order to make a 67.5-degree angle on the ecliptic plane. If we use the old 67.5 point, the angle is larger. And of course D, being on the circumference, is exactly at 90. We can't go wrong there. And the same goes for the other side. E has now moved further to the right, F has moved further to the right, and G has moved further to the right. And we reach Z2 on the other side of the globe. So how did I arrive at these points? Okay, I will show you the method. Of course, I had to jump through some hoops in order to get these points. But there are a couple of calculators online that you can use that convert between equatorial and ecliptic coordinates. One of them is the Frosty-Drew organization, frostydrew.org, and the other one is clearskytonight.com. They both have calculators that you can use. I actually downloaded this website and modified it a bit, and I added some extra fields. Of course, this is, I have to say that this is authored by Les Coleman, this utility, and I have to mention that he has to take credit for it. Use this number as the Earth's tilt. Wikipedia says is 23.436, and Google says the tilt is 23.439. I inserted the number of points I want from 0 to 180, and I generated the coordinates. What I do with these numbers then is I insert them in my Excel sheet. What I did was initially, before I understood the whole concept, I tried to find exact points on the ecliptic plane, but that had 22.5 degrees between them on the equatorial plane. This is of course wrong. It's wrong. And as you can see, yes, they have on the ecliptic plane, they have 20, for example, Z1 and A have 24.27 degrees between them. A and B have 23.15. B and C have 21.73. C and D have 20.82 degrees. So you see there's a discrepancy between these points. They're not evenly spaced on the ecliptic plane. They have between 4.6, 4.3% discrepancy between them, up to 6.5% discrepancy between them. No, we want them evenly spaced on the ecliptic plane. So after I fixed my program, you can see here that I chose points for generation that have evenly angular distance between them on the ecliptic of 22.5 degrees. Yeah, not this mess. This is a mess. This is correct. They have to have a constant 22.5 degree angle between them on the ecliptic. So my program generated points, and you can see here it gave me the R's, it gave me the longitudes and latitudes and in decimals. And then what I did to double check the points, I inserted them in another program here. that uses the WGS, World Geodetic System, to give me Cartesian coordinates for each point. Okay, and these are the X, Y, and Z for each point I generated. These then, X, Y, and Z for each of these points, which are Z1 here, A, B, C, D, E, F, G, and Z2. Okay, so for each of these points, I have my Cartesian coordinates, and then I enter these Cartesian coordinates one by one in this applet at emathhelp.net, and this gives me the angles between two points. One point, second point, and then I get the angle between them. As you can see, the angles are pretty close to 22.5. 0.056% discrepancy, up to 0.079% discrepancy. Of course, the discrepancy may have been introduced because of this system that generates the Cartesian coordinates. I don't know what kind of ellipsoid maybe they have in this system, but the angles are good enough for our purposes. Okay, so after I have these angles, then we can go and check them on the NOAA website, on the NOAA Solar Calculator. So what was the outcome? We saw angles west of D were smaller than their longitude. 0, 22.5, 45, and 67.5. They were smaller by this amount, each one. But the angles to the east of D, they were larger than 67.5, 45, and 22.5. They were larger. The average angle is shown here. The average angle between A and G. The average angle between B and F. The average angle between C and E is shown here. The average angles are still larger. Larger than 0, larger than 22.5 by this amount. This is the average discrepancy. So we see that the angles are divergent. We still see a divergence. The angles are not parallel. The angles are not converging towards a point at D. The angles are divergent, still divergent. Even so, while I was on the NOAA website, I noticed that if I used a time of 6 a.m. plus 1 minute and 40 seconds at our latitude of interest at 90 degrees east and 23.431512 north, even at the tilt angle that we chose, I noticed that at this time, that's 1 minute and 40 seconds later than what I used, I saw that the angle of elevation of the sun at this location was higher than 89.62. It was almost 90 degrees. So I thought to myself, I'm going to use this time instead of 6 a.m. GMT. I'm going to use this time and get a new set of values. So these are the values that I got. I got for 6 o'clock 1 minute and 40 seconds in the AM. For all my points, I got these values. And these values seem very balanced. Much more balanced than these numbers. I got 22.48, 22.54, 45.02, 67.510, 89.99, which is a much better sun elevation for that area, for that time of year. 67.51. These are balanced perfectly. It seems like I hit the spot, you know, I hit the midpoint exactly where all the elevation angles are balanced across the board for all my points from Z1 to Z2. The discrepancy between them is shown here, and it's obviously balanced also, perfectly balanced. The average angle between each point, of course, because they're equal, this is also balanced. And the average discrepancy is the actual discrepancy. All right? But we still see the same problem. Okay, I'm gonna disregard Z1 and Z2 for obvious reasons of refraction. But for the other points, we see increasing divergence from the middle. Okay, granted, the divergence is very small, 0.04 degrees at the 22.5 longitude is not much. 0.02 at 45 degrees and 0.010 at 67.5 degrees. But even so, these are divergent angles. They're not convergent angles. They're not even parallel angles. These are divergent. They're diverging from a midpoint. And you can't get better values than this. I did everything I can to find the perfect values, and these are the perfect values. We see divergence, maybe not as much as I thought initially, but still, we don't get parallel rays of sunlight reaching the Earth. They're not parallel, they're close to parallel, but they're very slightly divergent away from a midpoint. And on top of that, please bear in mind that these values are refraction corrected. They do not contain refraction. So what can I say? I think this is the end of this project. I have done all I can to find true and correct values. These are them. All I can say is that somebody has to do some field work and get some samples using a theodolite. Go on location at the right time and take measurements. I find it very strange that we cannot triangulate the sun. We cannot even get parallel rays of sunlight. We get divergent rays. So in closing, I want to thank everybody who offered their comments. I want to especially thank Emmy Zodiac. 8 months ago, he mentioned that I have a discrepancy in my angles. Okay, and I also want to thank Streets of Justice, who mentioned a discrepancy at the 0.5 degree angles a few days ago. And these are basically the people that pushed me to look at my angles again. So thank you very much for watching, and I hope you enjoyed the video. Have a nice day, and God bless you.